Hello everyone. This is a project of pattern recognition. My name is Edi Huang. My topic is applying BERT to machine reading comprehension. Machine reading comprehension is a task that tests how well a machine understands natural language by letting the machine answer questions based on a given task. There are four types of MRC tasks. The first one is a clause task. Clause task, also called the gap filling test. It is usually used in tests to access the language ability of students. Inspired by this task is used to measure the ability of machines to understand neutral language. And the second is a multiple choice. Uh, although I mean the multiple choice is another machine reading comprehension question inspired by the language uh, pro inspired by the language proficiency test. It requires uh, selecting the correct answer from the candidates based on the test text based on the context provided. And the third one is a span extraction. The uh, span extraction is that given the task, given the context and the question, this task requires the machine to extract a piece of uh, a piece of text from the corresponding context as the answer. And the fourth one is free answer. Compared with clause and multiple choice question, uh, free answering is the most complicated because it has no restriction, restriction, restrictions on the form of answering question, and it's more suitable for real application scenarios. So the full name of the BERT is bidirectional encoder representation from transformers. Um, the encoder of two-way transformer because the decoder cannot obtain the information to be predicted. Actually, let's talk about the transformer model. The transformer model are making use of enormous amounts of unlabeled data and training them with supervised learning task. One of the difference between BERT and prior methods of pre-training transformer models is a use of bidirectional context for language modeling. The most common form of language modeling with this large amount of unlabeled text like Wikipedia data is to sequentially predict the next word in a left to right traversal or do right to left as well to form the representation for word token. BERT instead masks intermediate tokens in the sequence for the for the prediction task, making the name of the bidirectional encoding. So we can use BERT to learn language translation, question answering, sentiment analysis, task summarization, and many more tasks. Turns out all of this problem requires the understanding of language. So we can train BERT to understand language and then fine tune BERT depending on the problem we want to solve. Training of BERT is done in two phases. The first phase is pre-training, where the model understands what is language and context. And the second phase is fine-tuning, fine-tuning BERT to learn specific tasks. Okay, so let's explain the transformer model architecture. See, we want to train this architecture to convert English to French. The transformer consists of two key components. So the left is the encoder and the right is the decoder. The encoder takes the English word simultaneously and it generates embeddings for every word simultaneously, like going this way. These embeddings are vectors that um, encapsulate the meaning of the word. Similar words have closer numbers in their vectors. The decoder takes these embeddings from the encoder to do this line and the previously generated word of the translated French sentence. And then it uses them to generate the next French word. And we keep generating the French translation one word at a time until the end of the sentence is reached. What makes this, um, I mean, the appealing part is that we can physically see the separation in tasks. The encoder learns what is English, what is a grammar, and more importantly, what is a context. The decoder learns how to English word related to French words. Both of these, even separately, have some underlying understanding of language, and it's because of this understanding that we can pick apart this architecture and build system that understand language. We stack the decoder and we can get GPT transformer architecture. Conversely, if we stack just the encoder, we can get a BERT. Okay, so BERT learns language by training on two unsupervised tasks simultaneously. They are the first one is masked language modeling, and the next sentence prediction. For mass language modeling, BERT takes in a sentence with random words filled with masks. The goal is to output this masks token, and this is kind of like filling in the blank, like we said, the types of clot, the reading comprehension task. It helps BERT understand bidirectional context within the sentence. In the case of next sentence prediction, BERT takes in two sentences and it determine if the second sentence actually follow the first in kind of what is like a binary classification problem. This helps BERT understand context across different sentences themselves. The fine-tuning phase, um, so we can now further train BERT on very specific NLP tasks. For example, let's take question answering. All we need to do is replace the fully connected output layer of question we want. Then we can perform supervised training using a question answering as a data set. It won't take long since it only the output parameters that are learned from scratch. The rest of the model parameter are just slightly fine-tuned. So as a result, the training time is pretty fast. The input is a set of two sentences with some of the words being masked. Um, each tokens is a word, and we convert each of these words into embeddings using pre-trained embeddings. This provide this provides a good starting point for BERT to work with. Now on the output side, the C, you can see the left top. The C is the binary output for the next sentence prediction. So it would output 1 if sentence B follows sentence A in context, and 0 if sentence B doesn't follow sentence A. Each of these T's, these T's here are word vectors that correspond to the outputs for the language model of a problem. So the number of the word vector that we input is the same as the word of is the same as the number of the word vector that we output. On the fine-tuning phase, the input and the output layer we pass in the question followed by a containing the answer as inputs, and the output layer we would output the start and the end words that encapsulate the answer. Uh, Assuming that the answer is within the same span of text, now that's passed to the explanation. Um, this is a token embedding part. The initial embedding is constructed from three vectors. The token embeddings are the pre-trained embeddings. The, the main paper use word piece embeddings that have a vocabulary of about 30,000 tokens. The segment embeddings is uh, basically the sentence number that is encoded into a vector, and the position embeddings is a position of a word within that sentence that is encoded into a vector. Adding these three vectors together, we can get an embedding vector that we use as input to BERT. The segment and position embeddings are required for temporal ordering. Since all these vectors are feed in simultaneously into BERT, and language models need this ordering preserved. Okay, so next we talk about we're going to talk about the BERT output. The output the output is a binary value C. You can see here, and a bunch of word vectors. But with training, we need to minimize the loss. So two key details to note here. Um, all of these word vectors have the same size, and all of the word vectors are generated simultaneously. We need to take each word vector, pass it into a fully connected layered output with the output with the same number of neurons equal to number of token in the vocabulary. So that would be output layer corresponding to 30,000 neura in this case, and we would apply a softmax application. This way, we would convert a word vector to a distribution, and the actual label of this distribution would be one hot encoder vector for the actual word. And so we compare these two distributions and then train the network use the cross entropy loss. But note that the output has all the words even though these input weren't masked at all. The loss, though, only considers the prediction of the masked word, and it ignores all the other words that are output by the network. This is done to ensure that more focus is given to predicting these mass values so that it gives them correct. Okay, the next is example code. To implement the BERT, we need to first install the transformer package. It's a library in Python. The transformer library has a large connection of pre-trained model, which can reference by name and load easily. For question answering, they have a version of BERT large and BERT small that has already been fine-tuned for the squad benchmark. Okay, so for example, here's a question and the answer task. Question is how many parameters does BERT large have? And this is a answer task that is related to the question. We can find the answer from this task. Um, the BERT large is really big, blah blah blah. It has 24 layers uh, and an embedding size of 1024 for a total of 340 m parameters. Although it is 1.34 GB, so expected to take a couple minutes to download to your Colab instance. Okay, so we will need to run the BERT tokenizer against both the question and the answer task text to feed this into BERT. We actually concatenate them together and place the special this SEP token. It's a separate token in between. Okay, the programming part is part like this. And just to see exactly what the tokenizer is doing, so I print out the tokens with their IDs. This is all the tokens. Actually, you can see the one word is one token, and these additions are handled for us by the transformer library, and all we need is to specify 0 or 1 for each token. We've concatenated the question and answering already, but BERT still need a way to distinguish them. So BERT has two special segment embeddings, one for segment A and one for segment B. Before the word embeddings go into the BERT layers, the segment A embeddings need to be added to the question tokens, and the segment B embedding needs to add to each of the answer text tokens. These additions are handled for us by the transformer library, and all we need to do is to specify a 0 or 1 for each token. This is also the part of the programming. Okay, so right now we've already feed our example into the model. We can highlight the answer just by looking at the most probable start and the end word. Uh, this is the following plot is generated to show the start and the end score for this is a start word score for every word in the input the score, as you can see, is positive here, um, and it's very high for the token 340, and then it's actually negative for every other token. And the reason they are negative and positive is that for the purpose of designing the model and training it, we use the softmax. But when it comes time to actually evaluate the model, you don't actually need to perform the softmax step. We can just look at the product value. We are looking at the dot product value, so we could kind of apply softmax to all of these, and it would create a probability distribution. But this is enough to basically pick the correct answer, because the correct answer is the 340, this word. And this is the end word scores. The end is a little less concerned about this is corresponds to the token 340. This corresponds to the subword M. Um, it is less concerned. As we can see, we compared this four, but it's still we got the correct answer. It's 340 M, right? So how do we decide if BERT's predicted span is correct? Um, having having BERT predict an answer span is pretty different from having BERT predict a category. So this is a question: where did Super Bowl 50 take place? And there are three correct answers. They are all correct. The answer one, it's Santa Clara in California, and the second one is Levi's Stadium, and the third one is Levi's Stadium in the San Francisco Bay Area at the Santa Clara, California. All these three answers are correct. Um, our our span predictor is really just two separate token classifiers. One for classifying tokens as being the start of the span, and the other for classifying tokens as being the end. To train our model, we will tell it the start token specified by the squad dataset is the correct one and all the others are wrong. That we're train it on the exact match of the span specified by the training data. So as we can see, the squad test set follows the same JSON structure as the training set. Um, there, there are three correct answers for this only one question. Um, there are three human provided answers actually, and we they don't always agree. Since all three of these seems acceptable, we will compare BERT's prediction to all three correct answer and took the highest F1 score that BERT gets among the three. Okay, so this is actually the squad example title. This is a title of the articles. There are actually these numbers training examples. The squad dataset is stored in JSON format, which looks identical to Python direction to Python dictionary syntax. The examples are organized in the hierarchy. First by the Wikipedia articles they're from, and then the parameter within that article. The below loop will just unpack these examples into the single list of examples. So and another things we need to do is to decide on the truncation strategy for this data set. Let's just first look at the distribution of sequence lines after tokenize all the samples in the training set. I've chosen to use a maximum sequence lines of 384 in this notebook to match the length chosen by the Hugging Face implementation. In the first pass, we will use the Sentinel string technique and tokenize all of these samples with truncation or padding. To handle the three possible answers, we score our predictions against each of the answers separately. The pick and pick whichever answer best matches our prediction. So for each test sample, the highest possible score is 2. Then we use answer question function built by transformer library to feed the model. Um, there are two standard approach to score the result on the squad benchmark, the exact match, and the F1 score. This is a programming part to actually see the result of the accuracy. With a fully pre-tuned BERT large model, I got correctly predicted index. It's about 88%, and the average F1 score is really high. It's about 0.914. Okay, so that's all the example code. Thank you very much for looking to the end.